Today I want to show you some very important facts about this quantum phase transition that we are arguing that might occur in the Z2 quantum lattice gauge theory. Okay, so I remind you that our Hamiltonian is minus J, the sum over all our plaquette operators, minus G, an external field. And this is a Hamiltonian for our gauge invariant Hilbert space. So we think that there should be a phase transition because on this side, for J large, we have a fourfold degeneracy. And on this side, we have a unique ground state. So we think there should be something in between, although there is something weird because it seems that both these phases, from the point of view of a local order parameter, they're both paramagnets. But they have this very big difference that they have a different degeneracy, and this degeneracy on the J much larger than G as a topological degeneracy. That is to the 2G. Okay, so how do we know that there is a quantum phase transition? One thing that we can do is to use one of our duality mappings. So if you remember, we use the duality mapping to show that the Ising model, the quantum Ising model, is self-dual. Now we will again use a duality mapping, but we will not find that the model is self-dual, but it's dual to something else that we will recognize. So what we do is that we define two new variables that are defined on the dual lattice. So from the duality mapping from the links, we go to, so in 1D, we would go from the links to the sides, but in 2D duality, from the links goes to the plaquettes. Okay, so from the links, we go to the plaquettes. To do this mapping, so you also can guess it from the fact that there are more links than plaquettes. So to do this mapping, we need to freeze some degrees of freedom. And so how many do we need to freeze? We need to freeze the 2 degrees of freedom that correspond to the large loops. Okay? So we will be in the sector where WZ1 is equal to WZ2 equal plus 1. Okay? So we do the mapping in this subspace. We can do the mapping in any of these subspaces, plus or minus 1 for any, but we need to do it separately for every subspace. So then we will need to, check that whatever our conclusions are, they don't come from the fact that we're in this subspace. No, what I'm saying is that in this mapping, there is no way to map these degrees of freedom to a new variable in the mapping that I will be doing. because I will only have plaquette variables. Therefore, because our subspace does, our Hilbert space also contains these degrees of freedom, then we don't have a Hamiltonian for that. So we freeze them.
Oh, is that a chi we defined the last time?
Yeah, it's the chi, but then I call them W1 and W2 Z.
Okay.
Yeah, so these are it is these degrees of freedom. See, W1, Z, so it's the product of Z around here, and this W2, Z. W2, okay. Okay, so what do? So as a first variable, P, so let me call it mu1 of P, we choose BP. And now we want to define some string operator. So to define this string operator, we choose on the lattice 2 reference lines. Okay, so they can be anywhere. Okay, so let me choose these 2. Okay, so these are just 2 reference lines. And then I can define the string that goes from the first link on the reference line to the right until I meet some plaquette P. Or, for the same plaquette P, I could also come from here. Okay, now this is a bit short, but you see, okay? So now on this string, I can operate with sigma x. In this case, it would be only 1 sigma x here. You see? So let me define mu3 of P like the product over all the L greater than 0, greater than the origin, so moving either to the right or upwards, of sigma x L. So of course I have 2 ways of doing this, right? So I need another variable. So I would say that this way I'm moving in the x direction, this way I'm moving in the positive y direction. So I put a nu here. A nu has 2 values, either x or y. And then this becomes L so I can use this notation. I can say P P plus nu. So let me see if this is the no, I used this other notation. I start from the link L in that is either horizontal or vertical, and they move in the direction nu. Okay. And the product is until P. Okay? So in this case, these arrive until here, this P. So let me put P here. Okay, so let's see what algebra these 2 variables have. So you can easily see, because these are just products of sigma operators, that mu1 square is the identity, and the same for mu2 square. And also this thing that if mu1 is at P and mu2 is at P, you see it here. So mu3 is this string. It's sigma x, 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 x. Mu1 is z, 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 z. See, they overlap only on one link, and they realize sigma x and sigma z on that link. So they have the same commutation rule of sigma x and sigma z, therefore they're anti-commute. So again, we have proven that these variables realize the polyalgebra, and therefore they act on a two-dimensional Hilbert space that is a spin half. So in these variables, I have mapped the Hilbert space of spins half in another Hilbert space of other spins half. So whatever operator I write in terms of this variable will be a spin Hamiltonian. Yeah?
Sorry, what is mu2
Is it
Because it's a type of type. That's mu1 and mu3. Okay, so now let's write our Hamiltonian.
May I ask a question?
Yeah.
You said there is only one overlap between U1 and U3, but isn't that there are two overlaps? Like one the left line and one on the bottom?
Yeah, but those are two different mu3. So this is, let me use colors. Okay. So this is P.
Yeah.
Okay. This string is what I call, where I put the mu1 in the direction x, and this is mu1 in the direction y, and for every direction they anti-commute. Okay? They only overlap here. This one overlaps here, and this one overlaps. Okay. So let's write the Hamiltonian in the new variables. So in the new variables, notice that if I take sigma x on some link L, so I can label this link as the link that is between this plaquette and this plaquette. Following our conventions, this is the plaquette P, and this is the plaquette P plus X, right? So in general, any L can be written, it's actually what I used here, can be written like P plus nu. So notice that sigma x on the link L, so on this link P plus nu, so this is the same than saying L, can be written like mu3 P nu mu3 P minus nu. That is like saying P plus 1 in the new direction. So what I'm saying is that this plaquette and this plaquette have this link in common. So if I operate sigma, the string of all sigma x's up to here, so I'm doing x, 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 and then I do it again, but I stop here. All these annihilate the sigma x's, and I'm left only with this sigma x. Therefore, I get this. So you see that I can write my sigma x operator as an Ising coupling in the new variables. And therefore, my Hamiltonian can be written like minus G, the sum over all the P in both directions of mu3P plus mu, and then minus J, the sum of the BP that I called mu1. As you can see, because now these are just Pauli matrices that anti-commute, this is the quantumizing model in two spatial dimensions, not in 1D, not the one that we studied that you know how to diagonalize. That's very interesting. Now notice that because the mapping is manifestly non-local, not all the properties are mapped one into the other. So the fact that this model is topologically ordered doesn't mean that this model is topologically ordered. However, some spectral properties are. Yeah?
We don't need to include the constraint into the new Hamiltonian.
Yeah, you see, because it's exactly because we don't. So the constraint is neither present in the old Hamiltonian nor in the new Hamiltonian. The constraint is encoded in the Hilbert space. So I am only writing. So the thing is that this mapping is non-ambiguous only in each of these Hilbert spaces, in each of these subspaces. Otherwise, otherwise this mapping is not properly defined. Because you see, I'm using this not only as as operators for my Hamiltonian, but also to label my Hilbert space. Okay, so the value that this operator can have depends actually on this sector. So I need to freeze this sector. Okay, but the interesting thing is that we do know that this model has a quantum phase transition. We know that every Ising model has a quantum phase transition, which is symmetry breaking. And so we actually, the critical point, so this model, we don't know how to solve it analytically, but numerically, we also know what is the critical G. Okay? But only numerically, unfortunately. However, we know that there is a QPT, and now we can use the results of what we know. So what happens for G large? This part, G large. Okay. So in the model that is quantumizing 2D, for G large, we are in the ferromagnetic phase. Right? This is the model. When G is large, we are in the ferromagnetic phase. And this so the ferromagnetic phase of the quantumizing 2D corresponds to G large here, right? To the paramagnetic phase PM of the gauge theory. G small is the paramagnetic phase of quantumizing in 2D. It corresponds to the topological phase of the gauge theory. And now we can use the results on the correlation functions that we know from here, and then translate them in the new variables and see what happens. Okay, so what are these results? So in the first case, G large, it's the ferromagnetic phase, right? So this operator, mu3, is different from 0. So what does it mean in this language? So you see, although we think, oh, this is just a paramagnet, so it's boring. However, we know that this operator has an expectation value different from 0. But what is this? It's this guy. So this means that for G large, this string operator is different from 0. It's equal to this. But what does this do? This is a string. Okay? So what the string does, a string of sigma x's, right? So we are in the ground state, okay? Because we want to compute, these expectation values are computed in the ground state. What does this thing do in the ground state? The ground state is the state where all these quantum numbers are +1. Remember? This is the ground state of our model. Now we operate with this string. So you see that all these plaquettes, you flip 2 spins. So their expectation value cannot change, because the expectation value is the product of sigma z. But the endpoints. So I have, my ground state is all +1, +1, +1, +1. But now this operator creates 2 kinks, a -1 here and a -1 here. And I'm saying that for G large, the expectation value of this operator in the ground state is different from 0. So we call this a kink condensation. So there is a proliferation of these vortices for G large. What about G small? Let me see where I can write it. Here.
Sorry.
Yeah?
I not really understand why. Like here you said U3 is equal to the product of this string operator, like product of sigma x, but why do you discuss about the product of plaquette operator when you explain the kink?
No, I didn't say it's product plaquette operator. I just show you what is mu3. Mu3 is I'm just telling you what mu3 does. Mu3 does this. It's a string of x's. What is the effect of a string of x's? Is to only change the eigenvalue of the endpoints of the plaquettes, because every other plaquette that is in between is flipped twice, so that cannot change. So I'm not saying it is the product of plaquettes. I'm just saying that mu3, which is a product of x's, is only changing these 2 eigenvalues. So the G large phase is a kink condensation, and we know it by using the result that we have in the Ising model. Okay. So for G small, oh, and what about no, this is it. For G small, okay, G small means that we are in the paramagnetic phase of the Ising model. So this means that correlation functions like mu1p, mu1p plus, mu1q, they must decay exponentially in p minus q. Where psi, we know, is the inverse of whatever gap we have at that point. Right? Because we're in the paramagnetic phase. But what are the mu1? Are the BPs in our language. So in the topological, yeah. So you see, in the topological phase, our correlation functions, BP plus Q, also decay exponentially. So it would seem that we have realized what we were looking for, that in this phase, we have a degenerate ground space with a gap, it's degenerate, and we have exponentially decaying correlation functions. However, I'm putting something under the rug. So keep this in mind, because in 1 minute we will see what it is. What about other correlation functions? Because, you know, we could also look at these guys. These also are gauge invariant quantities, so I am allowed to take these correlation functions. Well, but these are mu3, mu3p, mu3p plus nu, and then mu3q plus nu. Well, and they annihilate everywhere but in between P and Q. So this must go. So this is like mu3P, mu3Q. No, it's incorrect. Doesn't matter. No, let me do it this way. I don't look at them as strings. I look at them as operators that are based on P. So this is a two-body operator that is based on P. And this is a two-body operator that is based on Q. Their distance is, again, P minus Q, maybe minus 1. So this must decay like e to the P minus Q plus 1 over xi. So all correlation functions decay of gauge invariant quantities that are the only quantities that we can measure decay exponentially. So where is that I am cheating? So now this is very, very important. So why? So I'm claiming, oh, we have this great result that in the topological phase, we have degeneracy, but we have exponentially decaying correlation functions, which was not happening when we had symmetry breaking. But why? So why, when you have symmetry breaking, this was not happening? Apart from the fact that we cannot use the Hastings theorem. the theorem about the decay of correlation functions. Okay, why, when you have symmetry breaking, yes, it was the result of the calculation that we have long-range order, but why it can happen? Apart from the result of the calculations. So the reason is this. Imagine, so you have some degeneracy, right? So you have L, that is the span of two states, psi1 and psi2. Okay. And now imagine that our local observables are such that in this Hilbert space, this guy has non-vanishing matrix elements. We know this happens for sure because when we have symmetry breaking, we know that the expectation value of this observable requires a non-vanishing value. So not all these matrix elements are 0, right? In particular, OMM is different from 0. Okay. So let me call this number alpha. So order alpha. Okay, it can depend on m. So, but it is of order alpha. Then you can always define these two states, the symmetric combination, and if you now compute the expectation value in the symmetric state of OI OJ, so if you just do it, this must go like alpha squared. It's a trivial consequence of these two facts. So you see, because there are two states that can be connected through a local operator, then there must, at least that symmetric combination cannot have exponentially decaying correlation functions. Okay? So here we see that there are exponentially decaying correlation functions. But here I'm cheating. Why? Because I am freezing my Hilbert space in one sector. So I am effectively saying the ground state has only one state, right? Because the degeneracy are those 4 states, but I'm using only one of them. So in order to see that we really have decaying correlation functions, we must be sure that this also happens if I am, for instance, in a symmetric combination of those states. Because if I am in a symmetric combination of those states, so I need to check. So in order to check that these have to go through this argument, I must just check that a local operator has or has not vanishing expectation values in this subspace. Because if it has non-vanishing expectation values in any of these states, then the argument goes through. And I'm screwed. So this seems very unlikely, right? It seems very unlikely that from every pair of states in my subspace, any local operator has vanishing expectation values. So this is exactly what happens, though. So this is, if you want, this is one of the fundamental characteristics of the gauge theory and of topological order, is this, that, okay, so we have our ground state, that now we know is the span of some state that is our ground state, and then W1x 0 W2x 0, W1x, W2x 0. What do I mean by this? So if you remember here, yeah?
Sorry for interruption, but I'm still not getting why choosing symmetric combination result in the proportional to alpha to the square. Why would it?
Just compute, just use this fact and choose M and L 1 and 2, put it in. And just see. I mean, it's, if you put your pen down for 3 minutes, you do it. But don't let me waste time for this, because it's really... Okay, so what are W1x and W2x? So let me go to this thing again. So remember, our 4 states are the states such that this can be +1 + 1, +1 - 1, -1 + 1, and -1 - 1. So how do I change this expectation value, right? If this is a spin, and I said, oh, this is like sigma z. What is its sigma x? Right? If I'm serious that this is a 2-dimensional Hilbert space, it supports the algebra of the polymatrices. So this is the object that has matrix elements +1 and -1, because it can have 2 eigenvalues. So what is the other guy? Well, the other guy is also a string, a loop, non-contractible loop. It's this one that carries sigma x. This is the only operator that anti-commutes with this one and still has to commute with all the BPs, remember? So it must be a loop, but cannot be the product if it is a contractible loop, it will do nothing to change our state. So it must be a non-contractible loop, exactly for the same reason. So this one anti-commutes. So in this basis, it will have a 0, 1, 1, 0. So this is our sigma x. So if I call 0 this state, the state with both are +1, then the other 3 states are these 3. Right? This one becomes +1 - 1, this one -1 + 1, and this one -1 - 1. Is this clear? Okay, so this is our ground state. And I want to show that for every 2 states in here, no matter what, so can be also combinations of them, doesn't matter, so that OMN in this subspace is 0. How is this possible? Well, first of all, it's not entirely true, because there are some operators that have a non-vanishing expectation value. Unfortunately, this expectation value is always +1. So in the subspace, they act like the identity. So because they act like the identity, still it's okay. This also goes through. I need, in order to have this, I need this guy to have different expectation values in different states. Otherwise, you will not be able to connect different states. So of course, BP is such an operator. BP in the ground state of any sector is equal +1. So, but this is okay. This is not an exception. So we just disregard this stuff. We really want to see what happens to other operators. Okay. So how do we do that? So we start with the so let me show you in this way. So in order to show that this operator cannot have different expectation values in two states, let me show you that its matrix elements between, say, 0, and 0 and 0, 1, where this is 0, 1, and this is 0, 0, must be 0. Okay, so how do we do this? Well, first of all, so in the whole topological phase, so for G small, so for G equals 0, you can check, you can just check that any operator would be 0. But why? So let's do it. So this is 0, 0, O, and then this is W1X. 0, 0. Now, you see, this is a product of X's. And this can be anything. It can be the sum. This is some algebra, right? So this is something like a sum with the sum coefficients. Something like this. It's a spin system, so they must be Pauli matrices. So this is just the sum with coefficients of some small products of Pauli matrices. So without loss of generality, just consider some product on a finite set of Pauli matrices. Let's say X and Y. So you see that because this is very long, right? This is a non-local operator. And this is some local operator with support on I. This product cannot be the identity. So it means that there will be some sigma x's outside of the support of I that are left. But then the expectation value of sigma x in 0, 0 is 0. We saw it last time because of gauge invariance. You remember? Expectation value of this guy, or also of this guy, of any non-gauge invariant quantity is 0 because I can write this in this way. This is my gauge transformation. Then I pass it on the other side, and I get minus x gg 0, 0, but this is the identity, so it must be 0. So this is 0, exactly g equals 0. But what happens when g is small? Well, when g is small, now my ground state is not this. We don't know what it is. So we do perturbation theory. So perturbation theory tells us that at the 0 order will be 0, because it's what we showed. Then let's look at the first order, the second order, and so on and so forth. Well, so if my Hamiltonian now is, I treat the G term as a perturbation. So at the first order, I would have something like this, O, G, the sum of sigma x. So G is a number. And I was forgetting I have a W somewhere. Here. But you see, if this was I local, this is only I plus 1 local. What happens at the n order in perturbation theory? So it's 0 again. What happens at the n order in perturbation theory? So we have this. Now things become interesting. Because if this is R local, let me use the word, the letter R. Now this operator is R plus n local. Sorry, R actually n, Rn local. Because no, the one that I'm exponentiating, this one. This is 1 local, so it will be still n local. But so let me generalize a little bit more. Let me perturb it not just with sigma x, but with any, not just sigma x, but could be sigma x, or any other gauge invariant thing that is R local. Okay, not 1 local. Okay, now this operator here will be n times R local. So you see that if nr is equal more or less to the length of W, I might have, in perturbation theory, some operator that actually annihilates this such that the expectation value is not 0. So at the n or n over, at the n equal to L over R in perturbation theory, I might have a correction. But you see now we have a G to the n here. So this value, so this is order 1 by definition. So this goes like G to the n. G is a perturbation, right? So it's a number smaller than 1. So this goes like e to the minus L over R. So you see the tunneling amplitude between any two states in my manifold is exponentially small in L. So in the thermodynamic limit, it's 0. So in other words, no local operators can connect any states in here, in this manifold. They are effectively disconnected. They live alone. So it is for this reason that, as a matter of fact, when I compute correlation functions of local operators, they don't see the presence of other states like this one can do. This one can see the presence of other states. You remember, it was our argument for decoherence. Sigma z can make me tunnel from psi plus and psi minus. That's why there is long range order. But here these things are not there. So they live alone. By the same token, so they are degenerate, right? So it means that the difference in energy is 0. However, when I add the perturbation, they may split. But this is the same argument. Because again, the degenerate perturbation theory works in the same way. And it's actually the same argument. It's really the same argument. If an operator has vanishing matrix elements, then it cannot, of diagonal, then cannot have different eigenvalues on the diagonal. So this means that this splitting, or I can just repeat the argument, the splitting would be proportional again to this expectation value. Because I have to diagonalize exactly this matrix in the degenerate subspace. But so this splitting also goes in this way. So we are rediscovering something that we know from first year of quantum mechanics, that the tunneling amplitude in perturbation theory and the splitting are are proportional. So you see that the degeneracy is robust. This is a very interesting thing. Okay. So before showing, because all this is for the gauge theory, right? We have used the gauge structure heavily, but we said it's a bit unnatural, right? It's very unnatural. So we could take all this like a mathematical game. So we want to make it real. So before doing so, okay, so in the notes, there are all the details. Just I want to mention that all this construction is not limited to the Z2 group. I can repeat exactly the same construction with every finite group, and then it can be extended also to continuous groups. But so if you want to do it with a finite group, let me proceed in this way. So remember, on every link, we had a two-dimensional Hilbert space that was spin 1/2. Now we put a d-dimensional Hilbert space that is the span of these states that I can call, let me call them like this, E1, d minus 1. It's just a basis in this space, okay? Then, and I put this on a square lattice, okay, just as before. Now let me define, instead of a group Z2, another group G, such that its dimension, the number of elements in the group, is equal to D. And now I can define the left translation of these states. So I want to define a representation of this group over these states. So what I can do is the following, is that I can label these states with the group elements, right? I can say, oh, this one is what I call the identity. Yeah, the identity of the group. That's why I called it E. And this one is what I called G1. And this one is what I called Gn minus 1. And this E, G1, Gn minus 1 are my elements in my group. Well, so what is the left translation? On a state that is labeled by some group element H is just what a GH. So I multiply the group elements as a group multiplication, and then I go see what is the state corresponding to GH. And the left translation is this thing. So you see, this is the equivalent of our sigma x operator. Sigma x operator was sending me from spin up, that was the identity, to spin down. So sigma x. But now I have more states, right? So these are like ladder operators that are cyclic. What is the equivalent of sigma z? So what is sigma z? Sigma z is the operator that is reading in what state I am. It's the operator that, if I am in 0, gives me eigenvalue plus 1. If I'm in 1, gives me eigenvalue minus 1. So the equivalent of sigma z is some other operator that we have 2. When we operate it on G, we get the delta. So we get plus 1 if we are in G. But before sigma z can only read it with one value. Now I can read it with many values. This reads whether H and G are the same or not. Okay, so with these ingredients, I can again define my star operators. So AN, that before we call the GN. So the correct way to define it is that first I take, remember this is like sigma x. I'm doing sigma x, sigma x, sigma x, sigma x. But now it carries this label G, right? So this would carry this label G. So to be very democratic, I average over all the G's. And the BP operator was something that was telling me if I have vortices or not. This expectation value is +1 when there are no vortices. So the equivalent thing to do is this. So I take the product over the links of a plaquette. This is 1, 2, 3, 4. With some group elements H1, H2, H3, H4. Okay? But I want H1, H2, H3, H4 to be such that their product is the identity. Because I want to have that as a reference point, that we have no flux. So I have the constraint H1, H2, H3, H4 equal to the identity. However, again, this would carry a label H1, H2, H3, H4. So I sum over all these labels. H1, H2, H3, H4, such that their product is the identity. So this is the generalization of these operators. And then my gauge constraint is this one. And this is my gauge invariant operator that I can put in my gauge theory. Plus other operators that would commute with this, that might be more difficult to find. So whereas the algebra in the Z2 theory of L and T is the easy Pauli algebra, so they square to the identity and they anti-commute, the algebra of these new operators is more complicated, and you find it in the notes. So it depends on the group properties, but it's a very well-defined algebra. So I can generalize all this. And tomorrow we will see why the generalization is useful. However, in the last few minutes, let me show you, because it's actually quite simple, how all this can be made real. Okay, so gauge theory made real. Okay, so to be made real, we need to be in H dot. The Hilbert space of the spins. So this means that we are not requiring that we only work in this unnatural subspace in which Gn psi is equal to psi. That, why the hell should be like that? So no, we don't require that. However, we want to recover gauge theory, so somehow we want to recover this. Well, not by chance, Gn and our Hamiltonian commute, right? So that is very useful. In particular, it commutes with the BPs. It's not by chance, otherwise it would not be the right Hamiltonian for the gauge theory. It must be gauge invariant. So what if I call it a TC, and I write my Hamiltonian, in this way. So here I rewrite the Hamiltonian for the gauge theory. But now I am in the total Hilbert space. So in principle, I also have states such that this is not true. Okay? So because now I have these states in which this is not true, so it's not true that Gn psi is equal psi, so it's not true that Gn is always equal +1, the eigenvalue. This is the operator, this is the eigenvalue. So in particular, it could happen that this guy has some expectation value different from 1. And this is a local operator. So I can put it in the Hamiltonian. So I can put it in the Hamiltonian with the coupling constant. So now I have all the possible states. Only some of the states will have this. Now what happens if I choose the coupling constants in this way? U much greater than J and G. This means, and in particular, I consider J quite greater than G. So you see that every time I have a state that such that its eigenvalue is not +1, I pay an energy U. Because I put a minus here. So the states in the ground state must have energy minus U. But every time I don't have this, I pay an energy plus U. So my spectrum is something like this. I have many states. Then I have all the states. Then I have my ground state that's for fold degenerate. This gap is 4J. We saw it last time. Did we see it last time? So consider H equals 0. The ground state is when now all these operators and all these operators have eigenvalue +1. So the ground state has energy 0 equal minus n, because we have n sites, U minus nj. Then I put a vortex. So a vortex goes from energy minus j, right, to energy plus j. So it's 2j. However, I can only put an even number of vortices because the product of these guys must be the identity. So this product must be +1. So if I put a -1, I have to put another -1. So the minimum thing I can do is to put 2 vortices, each of which pays energy 2j. So I get 4j. So this band that happens when I excite vortices, when I excite plaquettes, is gapped away 4j. And this is what happens when I start violating this constraint. Then now it's an energy constraint. And this is gapped away for U. So the low energy theory of this Hamiltonian in the total Hilbert space is such that these states are such that Gn psi is equal to psi. Otherwise, I would pay energy U. So the effective Hilbert space of the low energy theory is the gauge invariant Hilbert space. So you see, we are not constraining it by an act of God that says, oh, the states must obey this constraint because they are identical. It's not a gauge structure. It's an energy constraint. We just gapped away, we found a way to gap away the states that are not gauge invariant. Now, so what I'm saying is that these states, this is a real transformation. If I apply Gn on a psi, in principle, I get some other state. Unless the state is invariant for some reason under this operator. But this is a real transformation, not a transformation for the labels. So now it's a symmetry. I'm saying, oh, those that violate it actually are away. So now we have some symmetry. Okay? We have this thing that low energy is defined by this. And one of you last time asked me, and now is the right moment to answer the question, because now our degrees of freedom, of course I can use this basis, the basis of these quantum numbers. So the ground state means no vortices and no kinks in this operator. So now these guys must be all +1. I can call them charges, Z2 charges. So no charges, because a charge costs an energy 2U. So I could use the basis of charges and vortices, but it is instructive to see what it looks like in the original spin basis. So yeah, we know that these states are such that in this basis all the AN are equal +1. I'm calling GN. And the BPs are whatever. But I'm freezing these degrees of freedom. But what do they look like as spin configurations? We know that as a spin configuration does not have this property, right? So what kind of spin in the spin basis, what does this look like? Well, let's see. We kind of know how to do it. Because you remember, we already know that this subspace is the subspace in which I've taken any state and I have projected in this way. So for the sake of simplicity, let me take the state all spins up. It's a convenient reference state to do this. And so last time I just counted dimensionality, but I didn't look at this state. Let's look at it now. So if I expand this product, you see that I have the identity. Then I have the sum over all the GNs. Then I have the sum over all the pairs of GNs. And so on and so forth. All the 3, and so on and so forth. But you see, this is the sum of acting on all spins up. Okay, so you see that in the end we have the superposition of many different states. So there is a lot of quantum fluctuations in this state, in the spin variables. And tomorrow we will understand what are these quantum fluctuations. Okay.